Welcome. Today we're undertaking a detailed architectural analysis. It's important to state up front that this review is generated by artificial intelligence, curated for a technical audience requiring a considered, slow pace.
We're focusing on the real challenges in modern distributed systems. Often the standard best practices just don't apply when you face complex, real-world legacy situations.
Indeed. And that's why our source today is software architecture, the hard parts. Modern trade-off analysis for distributed architectures, a significant work by Neil Ford, Mark Richards, Pramod Sattilej, and Zhamak Dehghani.
These authors bring a wealth of experience, particularly in microservices and distributed systems. Their insights are invaluable.
Our aim here is to extract the core decision-making frameworks they present. We're looking at how to handle those novel, tough architectural problems where there's no easy answer, no established pattern fits perfectly.
It often feels less like finding the right answer and more like achieving what the authors term the least worst combination of trade-offs. That really captures the essence of architecture work.
Achieving that requires discipline. Chapter 15 gives us a foundational process for modern trade-off analysis. It's a three-step approach.
That's correct. First, you have to identify the parts of the system that are, well, tangled together, interdependent.
Step 1. Identify entanglement.
Second, you need to analyze how they're coupled. What's the nature of that dependency? Is it static, dynamic?
Understand the coupling mechanism.
And third, you assess the trade-offs. You look at the impact of any proposed change on these connected systems. It's about understanding the ripple effects before you make the change.
A very structured way to think about consequences. Let's start by setting the scene, looking back at the context discussed in Chapter 1. The software world has evolved quite dramatically.
It certainly has. We moved from that era of, shall we say, large, centrally managed, service-oriented architectures, the classic SOA model, towards the more granular world of microservices.
And this wasn't just a preference change. Technology fundamentally enabled it.
Absolutely. For a long time, the default was shared, centralized infrastructure. Think central ESBs, central databases. The game changed when open source, specifically Linux, became effectively free from an operational cost perspective.
That ubiquity was key.
It was, and it coincided with the rise of automation tools, Puppet, Chef, and others. Suddenly, you could programmatically create entire environments on demand.
That capability, spinning things up automatically, that's what really allowed the shift away from relying on those shared, often overloaded, central resources. It paved the way for distributed ownership.
Which leads us neatly into Chapter 2 and the concept of architectural boundaries, defined by the architecture quantum. This is a crucial idea.
Can you define that for us? What exactly is an architecture quantum?
Think of it as the smallest unit of your architecture that can be deployed independently. It's an artifact with specific characteristics.
Okay, what are those?
It needs high functional cohesion, meaning it does one thing or one related set of things very well. It also has high static coupling internally.
So dependencies within itself, like libraries, frameworks, OS services.
Precisely. And the third characteristic is synchronous dynamic coupling. The parts inside the quantum talk to each other directly, in real time, synchronously.
You mentioned static and dynamic coupling. That distinction seems vital. Static coupling refers to dependencies resolved before runtime.
Yes, things like build time dependencies, framework contracts, operating system requirements, deployment needs. They're static in the sense that they are fixed for that version of the quantum.
Whereas dynamic coupling is about runtime behavior.
Exactly. It's the interaction between quanta or components at runtime. Communication protocols, consistency models, coordination logic, that's dynamic coupling.
And the core insight here regarding quanta is?
A monolithic application is, by definition, just one single large architecture quantum.
Everything is coupled, everything deploys together.
Correct. So the entire goal, the challenge in distributed systems is to effectively break that monolith down into multiple, genuinely independent quanta.
The book emphasizes that data often represents the biggest hurdle here. Even in early distributed attempts, using a single relational database kind of hid the coupling problems.
It created a false sense of separation. Everything still depended on that central database schema and availability. Once you truly embrace bounded contexts, as microservices demand, you're forced to confront the inherent tension between data consistency and architectural decoupling.
And that forces the hard parts into the open. This brings us to decomposition strategies, chapters 3 and 4, often framed by problems like those the fictional Sysup squad faced with their monolith.
Yes, Chapter 3 looks at the drivers for modularity, why break things apart. Maintainability is usually a primary driver.
Because in a monolith, a change in one area can ripple unexpectedly across many others, making updates risky and slow.
Modularity helps contain those ripples. The authors introduce a useful metric concept, maintainability level, or ML. It suggests that components with high incoming, coupling many other parts depending on them, tend to have lower maintainability.
Makes sense. The more things rely on a piece of code, the harder and riskier it becomes to change it.
Beyond maintainability, modularity impacts performance, specifically scalability and elasticity. It's important to distinguish these.
Scalability being the ability to handle large, sustained loads.
Correct, over a longer period. Elasticity, though, is about handling sudden, massive bursts of load, often short-lived.
And smaller services help both.
They do, but elasticity particularly benefits from small services because it relies on a low mean time to startup, or MTTS. If your service takes minutes to start, you can't react quickly to a burst. You need fast startup times for true elasticity.
Good point. Modularity also impacts deployability.
Significantly. Breaking down a monolith reduces deployment risk. Instead of a big bang monthly release, you can move to smaller, more frequent deployments weekly, daily even, because the potential impact of any single release is much smaller.
But as Chapter 4 points out, you can't just start breaking things apart randomly. You need to assess if the code base is actually ready for it.
You need to understand the existing structure or lack thereof. This is where coupling metrics become essential tools. We look at afferent coupling the incoming dependencies.
How many other components depend on this one?
And efferent coupling the outgoing dependencies.
How many other components this one depends on?
From these, we can derive more abstract metrics. Abstractness, which is the ratio of abstract elements like interfaces or abstract classes.
And instability.
Right. Instability is the ratio of efferent or outgoing coupling to the total coupling. It indicates how likely a component is to be affected by changes in others.
The book then introduces a powerful visualization, the distance from the main sequence metric.
This plots abstractness against instability. Components should ideally lie close to a diagonal line representing a balance. If components fall into what the authors call the zones of uselessness or pain,
meaning too abstract and stable, or too concrete and unstable,
it's a strong indicator that direct extraction might be problematic. You might need significant internal refactoring first before you can cleanly pull out a service. You can't just wrap a mess and call it a microservice.
A very pragmatic warning. Now, what about those truly messy code bases, the big balls of mud where structure is minimal? Measuring coupling might not even be feasible.
For those situations, Chapter 4 suggests a pattern called tactical forking. It sounds drastic, but it's often effective.
How does it work?
Instead of trying to carefully extract the piece you want, which can be incredibly complex and tangled code, you clone the entire monolith. Then, for your new service, you systematically delete everything you don't need.
So subtraction rather than addition or extraction.
Exactly. In highly coupled systems, deleting code pathways is often far easier and less risky than trying to surgically extract them with all their hidden dependencies intact.
It's a counterintuitive but potentially powerful technique for legacy systems. For more structured code bases, though, the approach is different.
Yes, for code with discernible components, we look at component-based decomposition. This is a more methodical approach, often aiming initially for a service-based architecture, or SBA, perhaps as an intermediate step towards microservices.
What does that involve?
It involves identifying logical components within the monolith, perhaps sizing them using metrics like source lines of code or percentage of the total code base.
And then mapping dependencies.
Critically, yes. Analyzing the coupling between these identified components to understand the potential service dependency graph before you make the cuts. You need to verify that the logical structure you perceive actually exists in the code's interactions.
Okay, so let's assume we started breaking things apart. We inevitably run into the data problem. Chapters 1 and 14 remind us of the distinction between operational and analytical data.
It's a fundamental split. Operational data, or OLTP, is what the system needs for its immediate day-to-day functioning, transactions' current state.
While analytical data is for looking back, finding trends, business intelligence predictions, longer-term strategic use.
And Chapter 6 dives into why operational databases often must be broken apart in a distributed system, focusing on the data disintegration drivers.
What are the main pressures pushing us to split databases?
Two major ones. First, the shared database risk. A change to a database schema, maybe for one service, can inadvertently break another, perhaps older or less maintained service that also depends on that same table. It's a hidden coupling danger.
Figure 6.3 in the book illustrates that quite starkly.
It does. The second driver is connection saturation. In a distributed world, each service instance typically manages its own pool of database connections. As you scale out service instances, the number of connections hitting a single shared database can explode, quickly overwhelming it. This forces database separation.
Data ownership then becomes a key challenge, especially as Chapter 9 discusses, when multiple services have a legitimate need to write to the same logical data entity, maybe represented as a table.
The simple rule of the owner is the service that writes breaks down here. What if service A and service B both need to update customer address information, for example?
How do you handle that joint ownership?
The book suggests a couple of techniques. One is the delegate technique. You designate a single service, maybe a customer profile service, as the sole writer. Other services, like order service or shipping service, must then ask the delegate service to perform the update on their behalf.
So it channels writes through one controlled boundary.
Correct. The alternative is the service consolidation technique. If preserving atomic transactions across the data they both touch is paramount, you might actually merge the two services back together.
But that's a trade-off.
A big one. You gain transactional simplicity, but you lose independent deployability, reduce fault tolerance. If one part fails, the whole combined service might fail, and significantly increase the scope of testing. It highlights the trade-offs involved.
Now, what about accessing data owned by another service but just for reading? Chapter 10 covers this. The simplest way is just direct inter-service communication.
Service A calls Service B's API to get the data it needs. Simple to implement initially.
But the downsides,
Performance hits from network latency, potential security complexities for the call, and data transformation overhead. It also introduces runtime coupling. If Service B is down, Service A might be impacted.
the alternative is often replicated caching. Service A keeps a local copy of the data it needs from Service B.
This has strong advantages. Much better responsiveness for Service A, increased fault tolerance because it doesn't need Service B to be available for reads, and better scalability.
But caching has its own set of challenges.
Definitely. It's generally not suitable for data that changes very frequently, as keeping the cache fresh becomes difficult and expensive. Cache invalidation is famously hard. And managing the configuration and consistency of distributed caches, especially across different cloud environments or regions, adds significant operational complexity.
Shifting focus to the analytical data plane, Chapter 14 introduces the data mesh concept. This sounds like more than just technology.
It is. It's described as a socio-technical approach. It aims to decentralize analytical data management, moving ownership closer to the domain teams that produce and understand the operational data.
How does that work architecturally?
A key element is the data product quantum, or DPQ. Think of this as a component owned and built by the domain team that exposes their domain's analytical data in a clean, consumable, trustworthy way.
So it's like a dedicated interface for analytics.
Exactly. It's operationally independent but designed for high coupling via asynchronous communication like event streams or batch updates. This suits the nature of analytical data, which often tolerates some latency, unlike operational transactions.
Let's move back towards service design itself. Chapter 7 discusses granularity integrators. These are the forces that might push us to keep services larger or combine smaller ones back together.
They act as counterpressures to the drive for ever smaller services. The most significant integrator is often the need for database transactions.
Specifically, AC transactions. Atomicity, consistency, isolation, durability.
If a single business operation must have those strict ACD guarantees across multiple pieces of data, and that data gets split across services, you have a major problem. Trying to maintain ACID across service boundaries introduces enormous complexity and tight synchronous coupling. Figure 710 shows this clearly.
So the need for a single transaction often forces related data and logic into a single service boundary.
Or forces you to accept weaker consistency models if you split them. Another integrator is workflow and choreography complexity.
Meaning how services interact to complete a larger business process?
Yes, if a process involves a long chain of synchronous calls between many small services, it becomes brittle. The overall fault tolerance suffers because a failure anywhere in the chain can break the whole process. Performance and responsiveness also degrade due to accumulated network latencies, what the book calls transitive dependencies. Figures 712 and 713 illustrate this risk.
This leads into Chapter 11, which compares different ways to manage these distributed workflows: orchestration versus choreography.
Orchestration implies a central controller, a dedicated service that manages the steps of the workflow. It tells service A to do its work, then tells service B, then C, often handling logic based on the results.
What are the benefits?
It's generally better for complex workflows where you need to maintain overall state, query the progress, and handle errors centrally. The CSOP squad ticket flow example leans towards orchestration for its primary path.
And the alternative? Choreography.
Choreography is decentralized. Services react to events emitted by other services. Service A finishes its work and emits an event. Services B and C might both listen for that event and react independently, perhaps emitting their own events later.
The advantage here is decoupling.
High decoupling, yes.
Yeah.
Which typically leads to better scalability and responsiveness because services aren't waiting on each other directly. The downside is that tracking the overall state of a complex process becomes very difficult. Error handling and recovery across multiple independent event handlers can also be extremely challenging.
These coordination patterns become critical when dealing with what Chapter 12 calls transactional sagas. This addresses the core difficulty that true distributed AC transactions aren't really feasible.
Right. You lose the guarantees, especially atomicity and isolation, across service boundaries. So when a business request needs to span multiple services but still needs some form of transactional guarantee, like all succeed or none appear to have succeeded, it becomes a distributed transaction managed using the saga pattern.
Sagas rely on eventual consistency. How does that work in practice?
A common approach is the orchestrated request-based pattern mentioned. A central saga orchestrator sends commands to participating services sequentially. If each step succeeds, the overall transaction completes.
But what if a step fails midway?
That's where compensating updates come in. For every step in the saga that completed successfully before the failure, a corresponding compensating action must be executed to undo the work. If you created an order, the compensation might be to cancel the order.
The complexity here seems high, especially because there's no isolation.
That's the critical point. Because distributed transactions lap isolation, other services might see and react to the partial results before a failure occurs and the compensating actions run.
Like the SysUp squad example, where the analytics service might process a ticket-completed event.
Only for a later failure in the saga to trigger a compensating update that reverts the ticket back to in progress. Now the analytics data is wrong, and you need another mechanism, possibly another compensating event, to correct the analytics. It can get incredibly complex to reason about. Architects should aim to minimize the need for sagas whenever possible.
Finally, Chapter 13 looks at the contracts between services and how they influence coupling. We have strict contracts versus loose contracts.
Strict contracts, like those defined using gRPC with protocol buffers or JSON with rigorous schema validation, offer guaranteed fidelity. The producer and consumer agree precisely on the data structure and types.
The benefit is safety.
Safety and predictability, yes. The downside is brittleness. Even a small, non-breaking change by the producer, like adding an optional field, might require consumers to update and redeploy if their tooling is strict. It creates tight coupling.
Whereas loose contracts, like typical REST APIs, returning JSON name-value pairs without enforced schemas, are more flexible.
Much more flexible. Producers can often add new fields without breaking existing consumers. This promotes decoupling and easier evolution.
But there's a trade-off in safety, or what the book calls contract fidelity.
Exactly. With loose contracts, you lose the compiler or schema validation guarantees. You need external mechanisms to ensure the consumer doesn't break when the producer changes. Consumer-driven contracts are one such mechanism, essentially. Automated tests defined by the consumer that verify the producer still meets their specific needs. They act like an architectural fitness function.
The chapter also warns against an anti-pattern, stamp coupling.
This happens when a service passes a large, complex data structure, like a whole customer object, to another service that only actually needs one or two fields from it, like just the customer ID and email address.
Why is that bad?
It wastes network bandwidth, increases processing overhead for the consumer to parse the large object, and crucially, it tightly couples the consumer to the internal structure of the producer's large object. If the producer changes an unrelated field within that large object, The consumer might still be forced to update if their tooling or libraries are sensitive to the overall structure, even though the data they care about hasn't changed.
This whole exploration really drives home the point that simply following generic advice or best practices falls short in the face of complex distributed systems.
Absolutely. A deep understanding of coupling static, dynamic data coupling, recognizing those granularity integrators pushing back against decomposition, and carefully managing data ownership and access patterns is essential.
It's about analyzing the specific context and making informed trade-offs, not just applying rules blindly.
For anyone facing these challenges, we strongly recommend reading the source material itself, Software Architecture, the hard parts. It provides the necessary depth, examples, and context to really grapple with these technical complexities effectively in your own projects.
The detailed explanations and trade-off analyses are invaluable.
And perhaps the final thought to leave you with is this. The true value of a software architect in today's world isn't primarily about championing the latest technology or methodology.
It's more fundamental.
It's about becoming that objective arbiter of the trade-offs. It involves constantly analyzing the specific scenario, understanding the forces at play, and finding the most appropriate, often narrow, context for each decision to arrive at that least worst combination. That analysis, that judgment, that's the hard part, and that's where the real architectural value lies.
A powerful concluding thought. We hope this analysis has been insightful. We encourage you, our friends of the show, to subscribe and follow our material for further explorations.
We wish you a great day and happy architecting.